now we're going to be very vague. Maybe vague is not the right word. General. Okay, we're going to be very general. Okay, so given any quantum field theory, so like if I say given any QFT, I'll write a little bit fast. So I'm sorry if it's a little messy. So given any QFT, we can split it into sort of data into two different types, right? We can have local data,
Mm-hmm.
okay, and then there's also global data.
Okay.
So let's do some concrete examples. And as always, I'll just focus on 2D and we can use the language of CFT, but I should stress that the story that I'm going to describe to you works in arbitrary dimensions and doesn't have to talk about conformal field theories, okay?
Okay.
So local data. Okay, well, this is an example that's not in not necessarily in a conformal field theory, because this object doesn't really make sense in a conformal field theory, is the S matrix.
Okay.
So that's, describing scattering experiments. That's an example of local data. An example of global data might be something like the global structure of symmetry group, right? So
Mm-hmm.
the LHC will be able to tell you about the S matrix of the standard model, but it's highly unlikely to ever tell you about the whether or not the gauge group of the standard model is SU3 times SU2 times U1, or that mod Z2, mod Z3, mod Z6, or none of the above. Okay. A concrete example of local data is something like the operator product expansion. Okay. And then some global data is something like 't Hooft anomalies. And hopefully that's clear because the global structure of the symmetry group and 't Hooft anomalies are all kind of captured by this fusiony data that I nattered about. So, you can kind of see that those are on different footings. And then perhaps the most concrete example in the case of a 2D CFT is local data is captured in the chiral algebra,
Mm-hmm.
right? Which is, roughly speaking, it's vertex operator algebra.
Mm-hmm.
Okay, the vertex operator algebra describes it. And the global data would be something like the modular invariant, right? Because there are some theories that have the same chiral algebra, left and right moving chiral algebra, but different modular invariants. Okay.
Fused differently, yeah.
Yeah. So as a concrete example, if you imagine at C equals 4/5 in 2D, right, there are two bosonic unitary minimal models, right?
Okay.
There's the tetracritical Ising model,
Mm-hmm.
tetracritical, and then there's also the Potts model.
Mm-hmm.
Okay, and these are called the A type and the D type sometimes in the literature. Okay, and so their shtick is that these theories have the same OPE because they have the same chiral algebra. Okay, so that means they have the same 3-point functions, all that kind of stuff. But they correspond to different modular invariants.
Mm-hmm.
Different modular invariants, so different collections of global data. Okay.
Right.
So now this sort of begs the question. Okay. This begs the question, what are, and as an exercise that's not important, but one could then start to study notions of relative and absolute quantum field theories, but that's a whole sideshow for itself, relative versus absolute. Okay. But the idea is so let me phrase this in the form of a question. Okay. What are all topological manipulations of a QFT? Okay.
Mm-hmm.
Now, what do I mean by a topological manipulation? I mean two theories, let's say, are related by a topological manipulation if they have the same local data. So have same local data, but different global data.
Okay.
Okay. But different global data. Okay. So in a concrete example, we would say that this tetracritical and this Potts model are related by a topological manipulation because they have the same local data but different global data. And in particular, maybe I shouldn't quiz you. The thing that relates them is a topological manipulation that relates them is gauging. Oops. Well, that's huge. Gauging the Z2 symmetry. Okay.
Okay.
Okay. So what are some examples of topological manipulations more generally, right? Well, it should be things that only affect the topological data. So if we think in 2D language, that includes gauging, aka orbifolding. Okay.
Mm-hmm.
So maybe I should just write them down. So there's orbifolding. I can stack with an SBT.
Mm-hmm.
Okay. And also this would include the GSO projection if you have a fermionic theory,
Mm-hmm.
or the Jordan-Wigner transformation if you have a bosonic theory with something that's Jordan-Wignerizable, so like a Z2 symmetry or something like that, right? But so
Mm-hmm.
basically everything turns out to just be captured in the notion of gauging or stacking
Okay.
with an SBT phase. Okay. And
Mm-hmm.
it's clear that this orbifolding doesn't affect the local dynamics because, I mean, it does talk to the original degrees of freedom of the theory, right? But the Z2 gauge fields themselves, if you're studying the Z2Ks, but I guess I could be studying the finite group gauge fields themselves are necessarily flat, so they have no local dynamics. Okay. But this will change who is local. So it'll change who's a twist field, who's not. Okay.
Mm-hmm.
Stacking with an SBT phase, obviously, same thing, doesn't change local dynamics at all, because what you're going to do is, I mean, you're basically taking a theory, which is essentially trivial. It's like a topological quantum field theory, and you're just putting it on top of the other theory. Okay.
Mm-hmm.
And so it doesn't even talk to the original local degrees of freedom at all. That's what stacking is, right? Stacking means you don't change the local degrees of freedom at all, and you're definitely not adding any. So really all it's going to do is it's going to change how the theory reacts to a background or something like that. And then of course you could do this first and then orbifold, and then that produces a new theory. So it does kind of mix them up a little, but still adds no local degrees of freedom. So these are all the topological manipulations of a theory.